Hello everyone, I am Rohit Agarwal and I am here to present our paper Mabnet, Master Assistant Buddy Network with Hybrid Learning for Image Retrieval. This is a collaboration work between Bio AI Lab at UIT, the Arctic University of Norway, and Indian Institute of Technology, Indian School of Mines, Dhanbad. Image retrieval refers to the task of returning relevant images from the database based on the provided unlabeled query image. Most of the approaches for image retrieval are either supervised or self-supervised. We aim to combine both supervised and self-supervised technique so that the self-supervision will complement the supervised approach with explicit semantic segmentation, improving the decision boundaries. Mabnet is a two-block buddy network where one is a master block and the other is an assistant block. Both master and assistant block are VIT based. Both master and assistant block learn individually via supervised learning using argfix loss. In addition, they compare their latent features for self-supervision using a distance metric, that is Kullback-Leibler divergence loss, where the assistant uses the master's latent feature as a reference for self-supervision. Instead of passing the original image to the model, we pass global and local crops of the original image to the model. Crops which covers more than 50% of the original image are known as global crops, whereas all the other crops are known as local crops. Global and local crops are passed to the master block to learn local global contextual embedding, whereas only global crops are passed to the assistant block to learn global only spatial information. Moreover, the weight of the master block is updated via weight transfer, where the parameters of the master block is updated as the weighted average of the parameters of the master block and the assistant block, as given by this equation here. The final loss of the Mabnet is given by the self-supervised loss, that is the KL divergence loss, and the supervised loss, that is the argfix loss of the master block and the argfix loss of the assistant block. During inference, only master block is used for prediction. The master embeddings are compared with the embeddings of the images in the database using a similarity function, and the relevant images are retrieved. Based on this similarity function, we can categorize the image retrieval models as without post-processing and with post-processing techniques. In general, a simple KNN-based model is used as a similarity function and falls under the category of without post-processing techniques, whereas other high-level post-processing techniques such as average query expansion, heat diffusion, offline diffusion, and CVNet re-rank used as a similarity function falls under the category of with post-processing techniques. Mabnet, when compared on without post-processing techniques, outperforms all the other models on Oxford and Paris datasets. The Oxford dataset is further divided into two more datasets, where the smaller dataset has 5K images and bigger dataset has 105K images. Similarly, Paris has 6K images and 106K images. Mabnet outperforms on all of these datasets compared to relevant methods. In literature, there is a new revisited datasets of Oxford and Paris. We compare our models on other relevant models applied on these revisited datasets and outperform all of them. Mabnet uses VIT as its backbone for both master and assistant block. Instead of VIT, ResNet and other CNN models can be used. When compared with ResNet 50 as the backbone of master and assistant, VIT outperforms ResNet. This is because convolution is a local operator, whereas transformer is a global operator that considers all the pixels and applies attention to find the important features. It is known that effective receptive field of lower layers for VITs are much larger than ResNets, which help them to incorporate more global information than CNNs. Thus, Mabnet with VIT backbone performs better than Mabnet with ResNet, as evident from the results. Mabnet, when compared on with post-processing techniques, outperforms all the other models. Mabnet also outperforms all the other models in each post-processing techniques. In the older Oxford and Paris datasets, offline diffusion gives good results, whereas in the revisited, offline diffusion and CVNet re-ranks give better results. We only use master block at the inference, but both master and assistant block can be used. We concat the master embedding and assistant embedding to compare it in the similarity function. This is referred to as Mabnet C, where C stands for concat. As seen from the table, Mabnet C outperforms Mabnets in all the in both post-processing and without post-processing, and also with respect to each post-processing techniques. Mabnet is 2 times faster than the Mabnet C at inference time because it has half the number of parameters. Thus, there is a trade-off between the performance and the inference time. This figure shows the progressive learning of master and assistant block. The master embedding are more general and is spread initially since it sees both the local and global crops. The assistant embeddings is also spread, but only to a part of the image, depending on the global crops passed to it. But the assistant block compares its nodes with the master block using self-supervision, and hence learns the localized information. This can be seen by the heat maps in the later epochs as it becomes more focused at one particular area. The master block in turn gets the localized information from the assistant block in the form of weight transfer and thus becomes more focused in later epochs, forming better decision boundaries. This is the reason for better performance of Mabnet. More information about Mabnet and its code can be found in this GitHub link. Thank you for listening to this presentation.